Communication complexity. We already saw in section 11.2.1 that solving the optimal allocation problem is NP complete even for single-minded bidders and thus certainly for more general types of bidders. However, as mentioned, in practice one can usually solve problems with thousands or tens of thousands of items and bids optimally or near optimally. Will it be possible to do the same for general valuations using some type of queries to the bidders? In other words, is the problem of representing the valuations an obstacle beyond the computational hardness? In this section, we provide an affirmative answer even if the auctioneer had unlimited computational power, then eliciting sufficient information from the bidders as to determine the optimal allocation would require an exponential amount of queries to the bidders for any query type. We present this lower bound in a very general model, Yau's two-party communication complexity model, and thus it holds for essentially any model of iterative combinatorial auctions with any type of queries. Let us first introduce this model formally. The model and the statement of a lower bound. The lower bound is obtained in Yau's standard model of two-player communication complexity. In this model, we consider two players, Alice and Bob, each holding a valuation function. We can restrict ourselves to the special case where the value of each set is either 0 or 1. Thus, the inputs are monotone functions, v1, v2, such that 2 to the m maps from the domain 2 to the m to the range that says only 0 or 1. Alice and Bob must embark on a communication protocol whose final outcome is the declaration of an allocation S complement that maximizes V1 of S plus V2 of S complement. The protocol specifies rules for exchanging bits of information where Alice's message at each point may depend only on V1 and on previous messages received from Bob, while Bob's message at each point may depend only on V2 and on previous messages received from Alice. No computational constraints are put on Alice and Bob, only communication is measured. The main result shows that Theorem 11.25. Every protocol that finds the optimal allocation for every pair of 0 or 1 variations, V1, V2 must use at least m choose m over 2 bits of a total communication. In the worst case, note that m choose m over 2 is exponential in m. Since Yau's communication model is very powerful, the lower bound immediately applies to essentially all settings where V1 and V2 reside in different places. In particular, to the case where the bidders rely to queries of the auctioneer, since a protocol with an auctioneer can be converted into one without an auctioneer by sending all replies directly to each other and having Alice and Bob simulate the auctioneer's queries and to any larger number of bidders, since the two-bidder case is a special case where all bidders but two have no valuations.